This is a review of Euler's method, section 2.5, number 1. I had a question about this recently. So let me just remind you, well, in this problem we are given this linear system, dx dt is equal to negative y, dy dt is equal to x. And but in vector format, we would say that it's a system. We have a vector y made up of the functions x of t, y of t. And on the right-hand side, we have a vector-valued function f made up of two functions, one for the x component, f of xy, and one for the y component, g of xy. In Euler's method, we're given an initial value together with a system and a time step. And Euler's method says you can approximate, and these squiggly lines are meant to say that we are approximating that our value one time step away, so x1, y1, is where we would go if we move delta t by 0.5 or some delta t, and we get to our new point by starting at our old point and adding delta t times the vector valued function on the right hand side, which is nothing more than just the slope in the x direction and the slope in the y direction. Here I'm reminding you that x sub 1 is just the function x evaluated at some time interval, and y1 after the first time interval delta t. When we write this component-wise, we have in general, this is our general form, that where you are at your k plus 1 time step is just where you were at your kth time step plus delta t times the slope in the x direction at the previous time step. Similarly for y, and again x sub k means that we're approximating where the function x is after taking k time steps of size delta t. Okay, so I'm going to go to the next slide and actually show you the numbers for this specific example. In this case, our slope in the x direction is given by the negative y values, and our slopes in the y direction are given by x values. The time step that we're asked to use in this problem originally is just 0.5, so it's a pretty clunky time step, but still we can get our numbers. I'm not going to walk through the whole table, but you will need a time column, an x sub k, y sub k, f, the slope in the x direction, g, the slope in the y direction, and then the new value in x and the new value in y. In this case, the slope in the x direction is just given by negative y of k, and the slope in the x direction is given by x of k, and the new value is just the new value of x is just the previous value of x plus delta t times the slope in the x direction. Similarly for y. So we are given at time 0, we're at 1, 0. But knowing 1, 0 allows me to say that this must be 0 because it's negative y, and this must be a 1 because it's x. And I can then move ahead and say, well, my new x value is just my old x value 1 plus delta t times the slope, which is 0, so we get a 1. The new y value is just the old y value 0 plus delta t, which is a half, times the slope in the y direction, which is 1, so we end up with a half. This new value is moved here to this position. Here's our new x sub k, and 0.5 is our new y sub k, and we start the process again. Our slope in the x direction is given by negative 0.5 because it's negative y. Our slope in the x direction is given by the current x value of 1. We compute the next x and the next y, and we place this 0.75 here, and we place this 1 here. And you see I've run through this for 1, 2, 3, 4 time steps. Okay? You'll see an example like this on your exam. same procedure, and just be careful with your steps. Good luck. Thank you.